There's also one interesting theorem that allows calculation of curve integral, of line integral of second kind, using double integral. So let us have some region D bounded by some curve L, and it's oriented in a positive way. Then integral by closed curve L p dx plus q dy can be calculated as double integral by region D, derivative q by x minus derivative p by y dx dy. But there are restrictions. This L has to be piecewise smooth, and dp by dy dq by dx has to be continuous inside region D, which also true for functions p and q. If we have continuous functions and their derivatives, then we can apply this formula. One more theorem that reveals more of wonderful properties of line integral of second kind. If we have functions p, q, r that are continuously differentiable in some region G, then we have four equal statements. First is that integral by L p dx plus q dy plus r dz equals 0 if it is an integral by closed circle, by closed border, and this closed curve lies inside region G. Next, statement that if we have some integral p dx plus q dy plus r dz taken by some curve L1, this will be the same as integral taken by some other curve p dx plus q dy plus r dz. Third statement: there exists function u that is continuously differentiable inside G, that w equals p dx plus q dy plus r dz is full differential of this function u, which means that du by dx equals p, du by dy equals q, du by dz equals r. And fourth statement, that if we have this form w, then dr by dy equals dq by dz, dp by dz equals dr by dz, and dq by dx equals dp by dy. Sorry, we have to get x here. Okay, so now we have these four equal statements, which means that if we have one of them true, then each other will be true. So if we have full differential of some function, as PQR, then integral by closed contour will be 0. Integral won't depend on way of integration, only on beginning and end, only on first and last point. And these equations will be true. What if we do have this form W? What if we do have this form W, which equals P dx plus Q dy plus R dz? And we have that this form is differential of u. How can we restore this function u? We can restore it in the next way. We can integrate it from m0, x0, y0, z0 to m, x, y, z, and we have to integrate p dx plus q dy plus r dz. And we can also restore it with some constant c, because we have derivatives here. But if we look at our theorem that we just stated, this integral won't depend on the way of integration, so we can restore it in next way. Integral from m0 to a, some point, we have this point m0, we move to point A, and later we move to point B. After that we move to point M, and we get m0a p dx plus q dy plus r dz plus integral ab of same thing, p dx plus q dy plus r dz plus integral from b to m p dx plus r plus q dy plus r dz. First integral, x is changing, but y is y0 and z is z0. T is changing from x0 to x. Here x is already x, y is changing, z is z0, so t will go from y0 to y, and finally we have a right to coordinate x, we have a right to coordinate y, but we still have to switch to z from z0, so t will be from z0 to z. So finally we will get integral from x0 to x p of t y0 z0 dt plus integral from y0 to y q x t z0 dt plus integral from z0 to z r x y t dt. This point m0 with coordinates x0, y0, z0 is some average point, but this point has to be point of continuity for functions p, q, r. So p of m0, q of m0, r of m0 are continuous. It is also can be rewritten for two variable functions, for two-dimensional case. If we have some region D, P and Q are continuous inside region D, and we have dq by dx equals dp by dy, which means this will be differential of some function. we'll get W as p dx plus q dy, full differential of function u in this region D. Now we can restore this function, moving from x0 to x, p of t y0 dt, plus moving from y0 to y, q of x t dt, plus some constancy, and also constancy here. Applications of line integral of second kind. If we have some vector field p I plus q j plus r k, then work for moving some point A to point B by curve AB. Following curve AB will be p dx plus q dy plus r dz. Also, we can use it to find area of some figure that is bounded by closed curve L. Area will be integral by curve L 1 over 2 x dy minus y dx, and this follows from Green's formula. And we can also find circulation of vector field A aligned by this counter L, which also be integral p dx plus q dy plus r dz.